Welcome to the Code Navigators. This is a show where we guide you through the sometimes dense world of the International Code Council.
Yep.
If you're studying for an ICC exam, or maybe you just need a faster way through a really complex code chapter, we're basically your map.
That's a good way to put it. Our mission here is, pretty clear. We go chapter by chapter through the ICC code books,
Methodically.
very methodically, and we explain what's in them. But more importantly, we give you the strategies to navigate them. We really want to break down the logic behind the rules.
And we get all this detail by using some AI-assisted generation, and this is the important part, it's all produced and overseen by a human code professional to make sure everything is clear and accurate.
Right. And before we get into today's topic, we have to go through our legal disclaimer. It's really important.
Absolutely.
So just to be clear, everything we're talking about here is for education. It's for educational purposes only.
It's not professional advice.
It is not professional advice. You always have to consult the official current edition of the code and, a qualified professional.
Like an engineer, architect, inspector.
Exactly, before you make any design or construction decisions.
Okay, and one more thing.
One more thing. We will not be stating any copyrighted material from the code text itself. We're purely focused on the organization, the intent, and the navigational logic. We're here to guide your study, not to replace the book.
Perfect. So let's get started. Today, we're focusing on one of the shortest, but maybe one of the most externally reliant chapters in the 2021 International Building Code.
Chapter 20, Aluminum.
That's the one. And if you're prepping for a structural exam, your mission here is pretty simple. You need to understand why this chapter is so short, what its limited scope really means, and where it sends you to find the actual engineering data.
Okay, so to begin, you have to realize that Chapter 20 is not some general guide for using aluminum in buildings. It's incredibly specific.
Right. The user notes at the very beginning make that clear.
They do. They establish a really narrow scope. This chapter only contains standards for the use of aluminum in building construction, where that aluminum is serving a structural function.
And that distinction is, well, it's everything, isn't it? Because aluminum is everywhere. I mean, it's in almost every single building constructed today.
It is.
So if it's so common, why would the IBC have a whole chapter that seems to cover such a tiny piece of how it's used?
It all comes down to code hierarchy and specialization. The IBC's main job is life safety and the structural integrity of the building.
The big picture.
The big picture, exactly. And aluminum is a complex material. It has really unique properties, depending on the alloy, how it performs under heat, its failure modes like local buckling.
Stuff that's very different from steel.
Very different. So the IBC sets the mandate for safety, but then it immediately delegates the really complex technical stuff to specialized industry experts. The exclusions in the notes basically draw that line in the sand. They tell you exactly what this chapter is not responsible for.
Okay, let's unpack those exclusions then, because for an exam, knowing where not to look is probably the fastest way to the right answer.
It often is, yes.
The user notes list 3 big categories that are excluded. The first one is specialty products, which sounds like things like aluminum storefronts or window frames.
Right. Think about it. Aluminum windows and storefronts are complete performance assemblies. They're designed and tested for thermal performance, weather resistance, glazing requirements.
And those have their own rules elsewhere.
They do. You'd primarily find them in IBC Chapter 24 for glass and glazing. They rely on external testing, the standards from groups like AMA, not the design rules here in Chapter 20.
So the key difference is that they aren't carrying major building loads, like from a floor or the roof.
Precisely. If a load is being transferred from the floor down a column to the foundation, that's structural. If it's just holding a pane of glass and keeping the rain out, that's a specialty product, even if it's made of aluminum.
Got it. Okay. Exclusion number 2 is architectural hardware. That sounds pretty broad.
It is. It can be anything from aluminum handrails and guardrails to decorative trim, or even certain fasteners in a non-load-bearing wall system.
Wait, a railing? I'm a little surprised by that one. Railings have to hold people back, resist a crowd leaning on it. That sounds like a load to me.
And you're right, they absolutely carry loads, but it's about the type of load and the intent of the code chapter.
Okay.
Aluminum handrails and guardrails fall under very specific rules for human safety and means of egress, which are mostly governed by IBC Chapter 10.
The egress chapter.
Right. They have to resist things like a 200-pound point load to prevent falls.
Yep.
But the design of that system is based on user safety, not on the material design rules for a major building component like a beam or a column that you'd find here.
Ah, I see. So the code kind of separates human interaction safety from building stability safety.
That's a perfect way to put it. And that brings us to the third exclusion, which I think trips a lot of people up on exams.
And that is?
The use of aluminum in HVAC systems.
Yeah.
Heating, ventilating, or air conditioning.
Right, because that's a classic split between the IBC and the IMC, the International Mechanical Code.
Exactly. It's a jurisdictional thing. Aluminum is super popular for ductwork and vents because it's so lightweight and it doesn't corrode.
Especially in like a humid environment.
Perfect example. But the design criteria for a duct, air pressure, leakage, fire resistance, all of that is in the IMC, specifically Chapter 6. It's not a building structure issue.
Okay, let's put that to a test then. A real-world scenario.
Yeah.
Let's say I'm putting a huge, heavy HVAC unit on a rooftop,
Okay.
and I need to build a structural frame out of aluminum tubing to hold that unit up off the roof deck. Which chapter governs the design of that aluminum frame?
That is the perfect test case. The aluminum frame itself, the one supporting the unit, that's a structural element.
Because it's holding the weight.
It's resisting the dead load of that machine, and it's also resisting huge wind and seismic uplift forces. So the design and material standards for that aluminum support structure are absolutely governed by IBC Chapter 20.
But the ducts connected to it.
The aluminum ductwork attached to the unit, or even the aluminum panels that make up the unit's housing, that all falls under the International Mechanical Code. It's a very clear line. If it's carrying a primary structural load, it's Chapter 20. If it's part of the mechanical system, it's excluded.
That makes perfect sense. So once we get past those exclusions, we get to the actual code text, Section 2001, General.
Right, and it's incredibly brief. It only has one subsection, 2001.1 scope.
And this one little subsection basically sets the mandate for all structural aluminum.
It does. It establishes the rules for 4 crucial aspects of how the material is handled through the whole construction process.
And those 4 are quality, design, fabrication, and erection.
Let's quickly go through why all 4 of those are so important. Quality is first. It ensures the raw material, the specific aluminum alloy, meets the right standards.
Because unlike steel, aluminum alloys can be wildly different, right? Like a 3000 series versus a 661 T6.
Wildly different. And if the quality of the alloy is wrong from the start, all the engineering calculations in the world don't matter.
Okay, next is design. That's the engineering itself, making sure the beam or column can handle the forces without failing or deflecting too much.
Correct. And then you have the 2 practical steps, fabrication and erection. And these are where the code really has to be strict with aluminum.
Why is that?
Well, aluminum is very sensitive to how you work with it. Fabrication covers what happens in the shop cutting, punching holes, and most importantly, welding.
Ah, the welding.
The heat from welding can completely change the metal's structure and reduce its strength. It's a phenomenon called the heat-affected zone. So the fabrication process has to be very tightly controlled.
And then erection is the final step, the on-site installation.
Right. Making sure the pieces are put together correctly, that the bolts are right, that any field welds are done properly, so that the final product actually matches the integrity of the original design.
This is a holistic approach, from the raw metal all the way to the final bolt being tightened.
Exactly. And that gives you a great navigation tip for any exam. If you're looking for general requirements on how to build with structural aluminum, you have to check the scope section first, because 2001.1 covers that whole life cycle.
Now, before we move on, there's that little code development reminder in the user notes. It says that any changes to aluminum structure are handled by the IBC Structural Code Development Committee.
And that's a really important detail. It signals just how seriously the code treats structural aluminum.
Because that's the same committee that handles concrete, steel, wood.
All the heavy hitters.
Yeah.
The foundational elements of a stable building. Yeah. By putting aluminum in that group, the code is saying, when you use this for structure, it's not a specialty item. It's a core structural material, and it's subject to the exact same level of scientific rigor and life safety review.
I think that helps explain why it's so complex. The people on that committee, structural engineers, architects, they know about all the weird things with aluminum, like galvanic corrosion if it touches the wrong metal, or how much more it flexes than steel.
Absolutely. That committee makes sure any new alloy or design method is properly vetted. It's the context you need to understand why the very next section, Section 2002, relies so heavily on other documents.
And that oversight from the Structural Committee leads us perfectly into Section 2002, materials. This is the moment where Chapter 20 really becomes, as you said, the ultimate gateway chapter.
It is. This is the point where the code tells you, to comply with our rules, you have to immediately go look somewhere else.
You have to leave the IBC book entirely.
You do. Section 2002.1, General, says that structural aluminum has to comply with two specific standards published by the Aluminum Association, or AA.
And those two critical references are AA ASM 35 and the really big one, AA ADM.
Yes, AA ADM is the Aluminum Design Manual. That's the main engineering reference for everything, properties, calculations, material specs.
And AA ASM 35.
That one is the Aluminum Association specification for sheet metal work in building construction. And for anyone studying structural codes, you just have to know those acronyms of what they are.
So the code demands compliance with these external documents. It's kind of fascinating how often the structural codes do this. Why doesn't the IBC just, I don't know, copy and paste the key formulas and strengths for aluminum right into Chapter 20?
Well, it really boils down to practicality and complexity. First off, just the sheer volume. The ADM, the Aluminum Design Manual, is a massive document.
Hundreds of pages.
Easily. It covers a huge range of alloys, tempers, connection types. And aluminum design is just fundamentally more complicated than steel because of its low modulus of elasticity and its sensitivity to local buckling, like we mentioned.
So putting all of that in the IBC would make the book just unusable.
It would just bloat the book. And second, the aluminum industry is constantly refining alloys and applications. By referencing an external standard, the code ensures it's always pointing to the most current accepted engineering practices without having to go through a whole code change cycle every time.
So the ADM is what's called a consensus standard.
It's developed by industry professionals, manufacturers, academics. It represents the best available science. By citing it, the IBC basically transfers the legal requirement for safety without having to become a material science textbook itself.
It sets the what, it must be safe, and then points to the ADM for the technical how.
That's the core principle of a gateway chapter.
Let's focus a bit more on the Aluminum Design Manual, the ADM. When an engineer is forced to go to this manual by Chapter 20, what are they finding that's so unique to aluminum?
Well, they're diving deep into failure mechanisms that are very specific to aluminum.
What's a good example? What's something an engineer might get wrong if they just tried to apply steel design principles to aluminum?
The biggest one is stability. Aluminum structures often fail by buckling, either the whole member or just a small part of it, long before the material itself actually yields.
So it's not about strength, it's about stiffness.
It's very often about stiffness and stability. The ADM provides incredibly specific and detailed formulas for calculating the allowable stresses based on how slender the different parts of a beam or column are. It has checks for local buckling of thin webs and flanges that are way more critical than for a typical heavy steel beam.
So the ADM gives you two main things. One, the raw data, like the properties for a 6000 series alloy versus a 7000 series.
Right.
And two, the specific methods for checking all those unique failure modes.
Precisely. And it also provides design options. It usually gives you both allowable stress design, ASD, and load and resistance factor design, LRFD.
Which are the two common modern design philosophies.
Correct. It gives the engineer the choice. So if an exam question asks about the design methodology for aluminum, the answer is found in the ADM, which is mandated by Chapter 20.
Okay, now how is that different from the other standard, ASM 35, for sheet metal work? Where does that fit in?
So if the ADM is the deep engineering manual for beams and columns, the ASM 35 is more focused on the practical side of sheet products.
So things like aluminum roofing or siding panels, flashing.
Exactly. It deals with things like fastener spacing, how to seal joints, material compatibility to avoid corrosion, all the practical details for thin gauge aluminum that are essential for making a building weatherproof and serviceable.
And Chapter 20 requires both because a structural frame might have sheet metal attached to it.
That's right. The frame has to be strong, which is the ADM, but the sheet metal parts of the system also have to be fabricated and installed correctly, which is the ASM 35.
This whole cross-referencing strategy is so important to understand. If an exam asks about, say, corrosion resistance of aluminum fasteners, the answer isn't actually in Chapter 20.
Not at all. But Chapter 20 is what tells you which standard you need to open to find that answer. It just confirms that the IBC's job is navigation, not to be an encyclopedia.
You could think of Chapter 20 as the Constitution, I guess. It declares that structural aluminum must be safe.
I like that. And the ADM is like the engineering Supreme Court, providing all the complex rulings and formulas to actually achieve that safety. So that brings us to the second critical mandate in Section 2002.1. This is the part that really closes the regulatory loop.
Okay.
So in addition to complying with those two aluminum association standards, the section says very clearly, the nominal loads used for the aluminum elements must meet the minimum design loads required by Chapter 16.
And this is the glue. This is what brings structural aluminum right back into the core life safety rules of the IBC.
It is.
Chapter 16 is structural design loads. That's where the code tells you the minimum dead loads, live loads, snow, wind, seismic, all of it.
The significance of this is huge. It means aluminum structures can't be designed in a vacuum. Chapter 20 sets the rules for the material and the design method, but Chapter 16 sets the mandatory level of performance for the building's location and its use.
Let's talk about how the fact that aluminum is so lightweight affects how you apply those Chapter 16 loads. It's not the same as with steel or concrete, is it?
Not at all. The difference is substantial. Let's start with dead load, the weight of the structure itself.
Which for aluminum is a huge benefit.
A massive benefit. Less dead load means you can have smaller foundations, less load on the columns below. The engineer has to calculate the dead load just like Chapter 16 requires, but the resulting force is just so much smaller.
But that same low weight can actually be a problem for dynamic loads, right? Like wind loads, which Chapter 16 makes us calculate.
That is absolutely correct. That's a critical point. Chapter 16 gives you the minimum wind pressure your building has to resist.
Okay.
When that pressure pushes on a very lightweight aluminum structure, like a long-span roof or a tall tower, that structure is much more susceptible to movement and vibration.
So it might be strong enough, but it would feel unstable.
Exactly. So while Chapter 16 tells you the force, the AAADM, which Chapter 20 points you to, guides the checks for serviceability and deflection. An aluminum structure might actually need to be oversized for stiffness, not for strength, just to control how much it moves under the wind loads from Chapter 16.
And then on the other side of that coin, you have seismic forces, which Chapter 16 bases on the building's mass.
Right, and that's the primary advantage of structural aluminum in a high seismic area. Seismic forces are proportional to mass.
Less force.
Simple as that. By using a lightweight aluminum structural system, you dramatically reduce the total seismic force that Chapter 16 requires you to design for. And that means smaller forces on your connections, your beams, your columns, your foundations.
So Chapter 20 and the ADM give you the tools to design a very light structure, but Chapter 16 is like the external auditor, making sure that whatever material you use, it can survive the minimum environmental forces for that specific location.
A perfect summary.
And because of all this, the rules in 2001.1, the loads from Chapter 16, the methods from the external standards, it means there's an absolute requirement for engineering calculations.
There's an irrefutable requirement, yes. You can't comply with this chapter without them.
You prove compliance entirely through detailed engineering judgment and math. The engineer has to perform very specific calculations for strength, stability, deflection, you name it.
Right. They have to prove that their proposed aluminum beam, for example, will safely resist the required loads, and they have to do it using the formulas and properties from the ADM standard.
And those calculations have to cover every possible way it could fail.
Every potential failure mode. For instance, if you're designing a thin plate, you have to show it's strong enough for the Chapter 16 load, but you also have to show it won't fail from something like localized web crippling or some other instability, using the checks defined in the ADM.
And as we said we have to emphasize for anyone listening, a calculation is required, but we're not going to explain the math in depth or give examples of the equations.
No.
Our focus here is on helping you recognize where the code demands this kind of rigorous analysis. And for structural aluminum, that demand is woven all through sections 2001 and 2002 by pointing to Chapter 16 and the Aluminum Design Manual.
And if you're taking an exam, that structure is vital to understand. If a question is about the capacity of an aluminum member, Chapter 20 is where you start, but it immediately sends you somewhere else for the actual solution.
That reliance on Chapter 16 also seems the common place to make a mistake. An engineer designing a connection for an aluminum column can't just look up aluminum properties.
They can't. They first have to go to Chapter 16 to find out what forces, wind, seismic, gravity, that connection has to resist. Then they go to the ABM to design a connection that's strong enough for those specific forces.
And aluminum connections can be tricky.
They can be very complex. They might involve specific bolting patterns or critical welding. So often the connection design is the thing that controls the size of the members. The calculations have to prove that connection is strong enough for the Chapter 16 demands.
It really changes your perspective. You're not just reading a few pages in the IBC, you're realizing that Chapter 20 represents an entire specialized body of engineering knowledge that becomes mandatory.
So to summarize our look at IBC Chapter 20, it is a highly efficient chapter, precisely because it is a definitive gateway chapter. It defines the structural scope, and that's about it.
Right. It sets really clear boundaries by kicking out all the high-volume, non-structural uses like storefronts, architectural hardware, and all the HVAC components.
Which are all governed by other specialized codes, like the IMC or other chapters in the IBC itself.
Then it immediately points you outward to the specialized industry-accepted references, the AA-ADM and the AA-ASM 35.
It does that for all the technical details. Material properties, design methods, fabrication. It ensures that aluminum design is always using the latest consensus standards.
And, maybe most critically, by forcing compliance with Chapter 16, it makes sure that even though aluminum is a lightweight, specialized material, its structural parts have to stand up to the exact same minimum dead, live, and environmental loads as any other material.
And for you, the person studying this, mastering Chapter 20, really means knowing exactly when to stop looking in the IBC and where you need to go next to get the detailed technical information.
We really hope this structure helps you navigate the code books with a little more confidence and efficiency. Your study and preparation are so important, and we're committed to bringing you this kind of focused code analysis.
And if you found this breakdown helpful and you want to support us creating more content like this, covering all the ICC code books, you can do that by visiting the Patreon link you'll find in the show description. Your support really does help us keep doing this.
It really does.
So let's leave you with a final thought to mull over, one that builds on what we just covered about the exclusions.
Okay.
We noted that Chapter 20 kicks out non-structural aluminum used in HVAC because that stuff is handled by the mechanical code.
Right. Things like aluminum ductwork and vents.
Exactly. Now, given that the use of aluminum in these advanced systems, like specialized fire-rated ductwork or vents in corrosive environments, is always expanding, you should be thinking about this. Which specialized ICC mechanical code chapter today is providing the detailed specs for those things? Not just for performance, but for material thickness, how joints are made, fire resistance ratings. Which code book and chapter provides the equivalent detailed guidance to the ADM, but for all those mechanical uses?
Something to think about as you expand your studies beyond just the IBC's structural focus.